Okay, well, we'll get going here. This morning is the first of the 2013, looks like people can hear me, so 2013 session. We have 7 energy-related webinars. This morning we're going to do animal housing. This is part of a SARE grant for professional development, and also with some funding from the State Energy Office here in Wisconsin and the U.S. Department of Energy. So I got a lot of slides here. I tried to cut these down. This was initially, we gave this seminar about 18 months, 2 years ago, and I'm not sure how they fit it all in, but we're going to try. So basically, we're going to talk about mostly here this morning is ventilation. And we're going to go look at general ventilation, and then we're going to look at swine, poultry, and dairy. And hopefully, if you've got some questions, we'll have time to answer them. So the first thing about ventilation is, if you want a ventilator or you're looking at ventilation, you have to have an air exchange between the inside and the outside. Just moving air around within a building is not considered ventilation. So you have to exit air through outlets or exhaust fans, and air has to enter through inlets in order to exchange the air. And this can be caused by mechanical fans in a building, and we can do that in a number of ways, or natural ventilation. And we'll talk about each of those. So I already mentioned that mixing fans or cooling fans, where we're trying to move the air around and not have dead spots, that's not considered ventilation. That's basically stirring or providing a cooling effect. And we're going to come back to that in a little bit. So environmental control systems. Basically, the reason we're ventilating is to supply fresh air and oxygen, to remove moisture and gases, remove heat, and maintain air quality. And that usually means ammonia level. Sometimes dust, but usually it's ammonia level. When we look at the reasons we need to ventilate, moisture is up there, heat is up there during the summer, but in the wintertime, we have a minimum ventilation rate, and that's usually tied to air quality or moisture, depending on the species and stuff. So in the cool weather, we may have to heat the building if we're using pork or swine, and then we have to cool the building in hot weather. The goal of any environmental control system is uniform conditions throughout the building. So you don't have dead spots or bad spots. Ventilation, I mean, we're looking, we kind of mentioned for environmental conditions or controls, we're looking at temperature, we're looking at humidity and air quality. And that is impacted by the number and age of animal species. So if you have chickens and pigs and cows, they're all going to be different based on weight and age of the animal. It also is affected by the manure handling system, especially when we get into poultry. You're going to see that. We've got some examples there, and the ambient temperature. The higher the ambient temperature, the more ammonia is given off, and so we may need ventilation that way. And if we get higher temperatures, we need to reduce the heat stress on the animals in that regard. So animal performance is related to good ventilation. If we have good ventilation, we're going to have high feed efficiency, which means good weight gain. If we're doing layer chickens, it may be egg production. It also has to do with the health and well-being. If we have poor air conditions, meaning high ammonia or gases, high moisture content, we can increase the chance of respiratory diseases within those animals. And that's, if you're a veterinarian and you walk into a barn and it's really damp and drafty, there's a good chance you're going to find respiratory diseases. So getting good air quality from a humidity and gas standpoint, especially ammonia, is very important. But from an energy standpoint, we don't want to ventilate too much, especially if we're doing supplemental heating. and we don't want to ventilate too little because that could add heat stress for the animals. If we ventilate too much, it could add heat stress too from the cold side. And the other thing is, when we're looking at the temperature of the environment, we need to make sure we have the right temperature for the age and species of animals that we're housing. And you're going to see when we're talking about poultry and swine, as they age, the temperature is going to go down. And then drafts and unplanned air leaks. If an animal gets chilled, it's going to start shutting down its immune system and stuff, or it's going to stress it if it gets chilled. So we want to reduce those drafts and chance of hypothermia. There is, for exhaust fan, which is required for ventilation, there's a relationship between the airflow that we can get out of that fan and the static pressure. You may find a fan that's 20,000 CFM, but you also have to ask yourself at what pressure difference between the inside and the outside of the building, which we call static pressure, is that at. Because as static pressure increases, the fan output decreases. So on the right here, we have a picture of a manometer, which is measuring the pressure differential between the inside and outside of the building. In this case, it's usually measured in inches of water column, and in this case, we have 0.05 of an inch of water column. So static pressure, the fan's going to have to work against, and basically it's the pressure difference between the inside and the outside of the building, as measured with a manometer. And for ideally, we're going to be in that 0.05 to a tenth of an inch of water column to get good ventilation. But the most important thing is the air velocity. We're usually going to use a slotted air inlet, and that's going to require a certain airspeed in order for that system to work. So here's a pictorial of a slotted air inlet. Let me get my pen here a second. Come on, colors. All right. So here's a slotted air inlet, and the object is the air is either going to come up through the gable or not through the eaves and in, but what you want it to do is go across the ceiling, and then it's going to entrain warm air into it, so it's going to temper it. If the static pressure, or which is related to this opening, you can see here we have an opening. We have it closed a lot closer here. If it's too wide and we have low static pressure, this air, especially in cold weather, is just going to come and drop, and then we're going to get drafts, and we're not going to get that entraining of warm air, at least not as much. So that's important. So if we get under 800 feet per minute, that tends to drop. It tends to be more like this. And this is for a slotted air system across the ceiling. If you've got a slotted air system down the wall, it's a little slower, but most systems are going to be across the ceiling. The other issue is if we get it too high, we're going to lower that air exchange, because as the static pressure goes up, static pressure going up is going to be related to the air velocity, typically, where you could get drafts and stuff because of excess air movement in a building. So one thing with exhaust fans is, when we look at the performance, is one nice thing is we have third-party testing. Best Lab, which is the University of Illinois, tests ag fans and publishes the data. You can go on their site. It's free, or you can buy a hard-covered book. And that test data is in airflow per unit of energy. So it's usually in CFMs, or cubic feet per minute per watt, and it's listed at a static pressure. And we'll look at an example of that here in a second. But one of the things to consider is not all fans are created equal. There's basically, if you look at that data, there can be a 2-to-1 difference in the same size fan in energy consumption. and this has to do with the type of equipment that's put on it and how well the fan's designed, and also the efficiency of the motor, which has a big effect. As fan diameter increases, so does the efficiency. So a 36-inch fan is not going to be as efficient as a 48-inch fan. A 12-inch fan will be less efficient than a 36-inch fan, and it's significant. I've got some numbers. We'll get a chart here in a minute. The other thing is diffusers and cones, which that's this little cone that's right here on the building. That can save 12 to 23%. If we look at the data across all the types of sizes of fans with diffusers and without, that's the number we get. Here in Wisconsin, we've looked at basically a high efficiency fan is going to be in the top 25% of those fans tested. And if we look at that compared to the bottom 75%, it's about a 20% difference in efficiency. So getting one out of that top 25% is going to be more efficient, and it will almost always be with a diffuser. The other thing to keep in mind, if you have a motor burnout on a fan, that motor has a big influence on the efficiency of the fan. So replacing it with a motor that is of the same efficiency will maintain the efficiency of that fan. So at times, even though they're more expensive, a higher efficiency motor is going to be more expensive because it has more copper in it. It's usually worth going back to the manufacturer to get a replacement motor, or at least making sure you have it, a similar efficiency if you go to a dealer, motor dealer, and buy that. So here's an example of the data you get from Beth's lab. Here's a description of what the motor includes. So this one has a guard and a discharge cone, and motor size and stuff. And so here's the static pressures as they go up. Your fan CFM goes down. And then over here you can see the CFM per watt also goes down as the static pressure goes up. Now typically we're in this 5/100ths to 1/10 of an inch, or maybe 1/8 of an inch of water column. That's typically where most barns are designed to operate. So here's a list that we put together here, basically looking at these will be considered in the top 25% of most fan sizes. And then I've got kind of a target number for what you should aim for to be in this top 25%. So this is the average of the top 25%, and this would be the minimum. So if you've got a 12-inch fan, you want to be 7.5 to be in that top 25%. So here's an example of what you might look at if you have too high a static pressure. So in this case, the building was designed for 8/100ths of an inch, and it's operating at about 2/10 of an inch. So we'll put that in some numbers just so you can see. So you can see all these go down in efficiency. So if we look at that at 8/100ths of an inch, our fan has 18.5. At 2/10 of an inch, it's 12.3. In this case, we had 80 fans. It's a layer barn. They're running continuously. So you got 364. You got 8,000 hours a year roughly. So they're going to use 1,432 kilowatt hours per day at 8 cents. That's about $115. So in this case, if we look at the summer, 90 days during the summer, that's $3,500 in savings just by getting this so it's operating back in the range where it should, not being excessive. So it can be a considerable savings. Stirring fans, they have their place. We typically use them in loose housing, especially with dairy, some with pork. But the object of these is to increase the air velocity to promote cooling. And in some cases we're going to use them in enclosed barns because we may have an area where we have poor air distribution, so if we can use them to move the air around. In greenhouses, we also use them to get, you keep the air uniform because we may have a heater running and we need to help distribute that air throughout the greenhouse. So that's another place, but that's not animal housing. But that's another place that we often use stirring fans. Best Lab, in the last 5 years, have developed testing for these, so there's not a lot of fans tested yet, but you can go to the site and get the data. You can't get the CFM ratings from a circulation or stirring fan because they're not enclosed. They're just blowing air out in the open with no static pressure, basically. So the test we use there is to look at the force that I put. So if you've got this this fan mounted and you got it running, it's going to have a force pushing it back as the air goes out this direction. So we're measuring that force, and we're using kilowatts, or the amount of energy that it's consuming, to look at how good a fan that is. And then we also look at where they're measuring the center velocity of that air, basically to give you an idea of how much of a cone shape or funnel shape that is, or column of air goes out versus how fast it diffuses. And so we've got the thrust of this is proportional to the airflow. So that's how we're gauging efficiency of fans. So here there's not as many fans tested. So here I'm using the top 50% versus the bottom 50%. So we've graphed them, and here this dotted red line is kind of the minimum I set to do. So if you're going out and buying a fan, try to get in this range, and you'll be in the top 25%. Now, another thing I want to point out is 36-inch fans, I had guards and without guards. So you can see the difference is quite substantial, almost 25% by having guards in there. So one that looks at the cleanliness of the guard, because if they're occluded, that's going to affect it. And if you can get away with it without a guard, which means it has to be out of reach of animals and people, so that usually means it's got to be 8-10 feet high. We're going to be more efficient if we have a fan without a guard. And all these littler fans, they typically don't have guards, so that's why they're lower. So that's just something to keep in mind if we're using stirring fans. But without a guard, they have to be high up out of the way. On the maintenance side, too, is belt-driven fans. If that belt is slipping, it's going to have less airflow. So here's a fan. This line is the Best Lab data. Here's an actual after it was adjusted, and here's it before it was adjusted. So again, you've got about 25%, 30% reduction at a low static pressure. And I think this isn't kill pascals, but I think this is about 0.2. You can see at a higher static pressure, that difference is almost 50%. So it's very important to keep those belts tight. Now, one thing I recommend is an automatic belt tightener. If you're buying a new fan, I would highly recommend you buy it with one. And if you can buy a retrofit for your fan, it just gets rid of a task, so you don't have to do it. Otherwise, they should be tightened about on a monthly basis. The other is dirty shutters. Back in here, there's shutters or louvers, and if they're dirty, it doesn't allow the air to go through it, so that can reduce airflow. And the other is blockage on the guard itself. It's just like putting a board in front of it. But it needs to be cleaned. Now, the shutters or louvers, they can be cleaned and they can be lubricated, but they should be lubricated with a dry lubricant. If you use oil or grease, it's just going to attract dirt and make them stop working that much quicker. The other attachments, we've talked about discharge cones. And here's the line for discharge cones versus having no fan, no shutter, just a fan with a shutter. In some cases, we have wind problems. So there's a manufacturer out there that's recommending hoods, basically, to deflect the air so it's not pushing directly against the fan. I mean, I've been in some barns where you have gusty wind out of that side that the fan's on, and it'll basically stop the fan. I mean, it's possible. And then when you stop the fan, you stop your ventilation. One of the issues with these hoods is that it's a deflection. It adds a pressure drop to there. And you can see that in the graph that we've got a big difference here between these. This is in without wind between those. So you're going to pay a price if you put a wind guard on every day because of lower efficiency. And of course, as the static pressure goes up, it increases. A better solution for this is probably to put in a windbreak. So this can become kind of a fence. So here's an example of a fence. 15 to 20 feet away. I might even go 30 feet away. The higher this is, the better. I mean, this is going to be pretty good because any wind coming through here, it's not going to be direct on the fan, but it still could affect it. So having this a little lower would be better. The other thing this does is it helps dissipate odors, especially if this goes from ground to ceiling. And this could be done with trees or something like that, but basically you're trying to move this air up so that it entrains with air coming across the building so that it dissipates the odors for people that will be downwind. So another way to do it without putting that cone in to affect the efficiency of that fan. And then we have just general maintenance. Here's a discharge cone that's gotten damaged, so we've got a safety issue because now the guard can't be put in place, and we've got open blades here. So from a safety standpoint and a performance standpoint, it's very important to keep the maintenance up and think about safety. So now we'll kind of move to swine and look at some of the issues with swine building. In this one, you can see the ventilation. This is a ceiling type drop where they have the air coming down through the ceiling, and then it dissipates either out one side or multiple sides across the ceiling. Energy production with the swine, typically it's going to be LP gas or maybe natural gas if you're close enough to a city, and electricity. And this 2 to 5%, and this is from a Minnesota study, is kind of the range of energy costs. Of course, it's going to depend on how much heating you do versus cooling. The big indirect energy use, though, in this is feed. 60 to 70% of our cost of production of producing a ham is feed costs. So anything we can do to affect the feed efficiency or the rate of gain of those pork through good environmental conditions will save energy long term because that's indirect energy, fertilizer, tractors, fuel to produce that crop to feed that animal. So here's some data from over a variety of years from Minnesota. It's going to depend on the year and how hot it is. As to, hotter year, we're going to use more ventilation. We'll use less heat in a warmer year. So there's an inverse relationship here. If you have a warmer year, you're going to use more ventilation, less heat, etc. So this will give you an idea of the costs for energy use. So this was for 1,800 pigs a year in groups of 600. And here's some electrical information coming out of Canada. So just kind of it's going to vary with the type of system a little bit. This wasn't a huge sample size, but this gives you an idea of the average amount used. So we've got a per sow here and then per hundredweight. And you can see some of these change because the finishing operation, you end up with a larger animal, so you've dissipated some of that heat versus a nursery animal. In the nursery stage is when you're using much of that heat or energy. So when we look at the costs for swine production, this is out of Canada again, 39% is ventilation. 21% was lighting, which we talked about in December. We've got creep heating, about 11%, and then we've got miscellaneous stuff. So, you know, 3/4 of this is the environmental conditions, either lighting or heating, and you know, roughly half of this has to do with heating in this case. So ways to control our direct heating costs, especially in a heated building where we've got cooler, cold weather. One is to reduce the ventilation rates, but we can't reduce them any more than what's required to maintain good air quality. So that's one, is make sure we're not over-ventilating for the size, weight, age, species of animal we're dealing with. Building insulation is another one. One, this is for condensate control, but also for unplanned air inlets, leaks from drafts and stuff. And I got a really nice picture when we get to poultry to show you the effect that can have on poultry. Environmental set points. Again, this gets back to temperature. Make sure we've got our temperature set points and our offsets, and when our fans are coming on, placed in the right areas so we're not overventilating or overheating, etc. And I already mentioned temperatures and fan efficiency. You know, make sure that we're doing the maintenance on those fans, and that we have the fans we've selected are high efficiency. And one thing I'll point out here I didn't talk about earlier on fan efficiency, sometimes you're better off buying a bigger fan because they're more efficient and putting a variable speed controller on it to basically be able to lower the output of that fan during cold segments or when you need less ventilation rates. Majority of the fan requirement is going to be during the warm season. So that is one way to do it. So here's kind of a heat balance. I probably should have had this before the last slide, but one thing you can see, the arrows are kind of relative to the amount of energy we use. So you can see the animals. We use this confined space, so we have a lot of heat off the animals. We have some supplemental heat. Our biggest loss of heat is through the exhaust air. So sometimes we can recover some of this. There are some systems, although it's sometimes a little cumbersome and costly to do that, but that is a possibility. But the building shell is minor, and this is actually almost minor compared to the amount of air being exhausted in some of these buildings. Been talking about minimum air quality and stuff. Well, every species there's a minimum airflow rate that's recommended depending on the species and size. So this would be in very cold weather. So you know, when your heat loss is low, this is kind of the minimum you're going to go to. So this is where all your heating is going to be required when it's really cold, but you still have to provide some ventilation for air quality. That's usually what, in low cold temperatures, that's usually what hits it. But then when we get to mild or hot temperature, then it's usually you're exhausting because of heat, excess heat, not because of air quality. The other thing I might point out is swine and poultry use a lot of unvented heaters or direct vent heaters where there is no exhaust or a stack. All the products of combustion are dissipated in the barn. They require fresh air be brought in to maintain the oxygen levels in that. So that requirement, based on manufacturer's recommendations, has to be added to these So I talked a little bit about conduction heat loss. The main reason we're interested in insulation, if we have 0 outside and 70-degree room inside, which actually is cold for some of our species, but at 34 degrees, we're going to have a 34-degree surface temperature, and we're going to get condensation at 25% relative humidity. So this would be like if you have, a house. If you live in a house and you get condensation on your windows, this is about the R value of your window pane from a single pane window. So that's why you get condensation if you've got a house that maintains temperature. If I put an inch of foam insulation on the outside of this, I increase my insulation value of that wall, by 5 times or so. So now my surface temperature is 62 degrees, and I get condensation at 75% relative humidity, which is more reasonable. So this is an issue from an animal standpoint and also a building integrity standpoint, because if I have condensation on that wall all the time, it makes for a damp environment typically. The other thing I'll point out is many of these in a swine building, very often you have a pit underneath the barn for the manure, and those require ventilation. So this is a pit fan for ventilation. So your ventilation is usually going to be split between pit ventilation and ventilation at the barn level or the animal level. This barn is showing a roll-up curtain, sidewall curtain, which would be probably used in a grower finishing type facility. And curtain management's an issue. If we're trying to heat this or maintain an environment, and we got holes in here, that's you can see there's 4 holes in here. They can happen for mice if these are down during the summer. The mice love to get into these sometimes. So keeping these in good condition helps our air quality and or our environmental system work properly. The other thing is if we're trying to heat the barn or keep or even use tunnel ventilation in the summer, these things will leak. Actually, let me back up here a little bit. This curtain is usually a lift up. It comes up and just hits up against or overlaps a plate up here. And on the end of this is basically a shield here. These are just loose on the end, so air can go over the top or around the end of these. And so they're not airtight at all. So if you're going to be where you need to heat this or you're trying to keep drafts out, one of the things we can do is fasten these edges down. So fasten the edges down there, fasten them across the top. The bottom's usually already fastened. If it's a pull-up curtain, sometimes they're drop-downs. But one thing we can do is go out of the greenhouse industry. They use these things called wiggle wire. So here's a picture of it. It's a channel. The channel is actually kind of shaped like this, and the wire would go in here and lock the plastic in place. So we can use that type of device to hold these down in the winter time. And the other thing we do is put another layer of curtain on. If we put 2 layers on, and especially if we blow this up or put a little air in there, similar to a greenhouse, we can cut our heat loss through that section of the building in half. So that can be an advantage. Another thing some people have used is this bubble wrap. You can put that inside or outside. It's about the same. It's going to be about the same reduction in heat loss as putting a double wall curtain on. It may be easier for some. It's probably a little more costly, but it depends what you're willing to use. Controllers. They are important from the fact that we're controlling temperatures, we're controlling fans, we've got inlets, maybe sidewall curtains we want to open and close, we've got lighting. In the summertime we may have misting or cooling systems and we can control all those through some type of controller. is the important thing is to make sure that we have, we're heating, and we're not ventilating. So here's a pictorial of a typical system. Down here we have our minimum ventilation rate that we run year-round, regardless, as long as there's animals in the building. And then depending on where the temperature is, it depends on what happens. So here, this is temperature. Over here we've got supplemental heat from the heating of the fan, and over here we've got ventilation. So, if we drop down to 68, this heater is going to come on. It's going to heat until it gets to the shut-off point. In this case, I've got it set at 72, and then it's going to stop. Now, if we look at the temperature of the building, after it stops, the heat may drift up here a little bit in temperature as the heat from the heater gets distributed through the building. It's not, basically instantaneous. What we don't want it to do is drift up so much that it triggers the fan, so then the fan comes on and takes that heat we just heated and takes it out of the building, and then you're going to get a drift. You could possibly get a drift here, and then the heater comes back on. That's called cycling. We don't want that to happen. So we need to make sure that this offset, the difference between the heater coming on and the fan coming on, is wide enough that we don't get circulation or cycling. And then if we, typically we have a system where we have, and this could be one fan or a group of fans, we typically will have one stage and maybe two stages for, mild temperature and hot temperatures, and many times we have many more stages depending on how the system is put together. So here's an example of a three-stage fan, and here I've put in multiple stages of heaters. Now, the heaters could overlap, and this is an example where I might go in, maybe I have some old heaters in this building, I might go in with a high-efficiency heater, but I don't size it to be able to heat the whole building. I size it for maybe 50% or 80% of the heating load of that building. And the reason I do that is because if I go for 100%, it's more costly, and maybe for the few hours of the year that I would need full heating or 100% of that capacity, it might only be a few hours a year, so it may not be cost effective. And since I want some redundancy in my heater, I just leave the old heater in there for redundancy. So in this case, you got this first heater. If it comes on and it can't keep up, it's not putting the temperature up, and the temperature dropped, in this case, to 65, then the second heater would come on, and it would run, and hopefully that would bring it up to at least, this is set at 69, and that would shut off, and then this number one heater might continue to run until it got up to 72. This is also a case where if maybe you have a wood, you want to do a biomass heater of some sort or some kind of renewable energy heating. You'd make that the primary heat and your current heating system your secondary heating. So that's another way to do that. And you can do that, control all that with a controller. This tries to show, I showed it earlier in a graph, but this tries to show as, here's my optimal conditions here. If I go above that, this is heating, this is fuel use, and this is electric. So this is fans versus furnace. As I go above that, I use more energy in heating, and I'll use less energy in cooling. So that's that relationship between heating and cooling. So one of the things we want to make sure is for the species we don't have it set too high. And one of the things that has been pointed out is the fact that finishing pigs, we often have the temperature higher than it really needs to be for the size of the animal. So I've already talked a little bit about this. Heating, cooling exhaust fans is one we want to make sure we don't have large temperature swings. So we don't want to have that heat, cool, heat, cool. We want to prevent cycling, and that has to do with that offset or the settings. The wider we can make that, the better off, or the less chance we're going to have a cycling, and the more energy we're going to save. We also want to make sure that temperature sensor is sensing what the animals require and are sensing. So typically we're going to want that near the center of the building and in a area where it's close to the animals, but not so they can get to the sensor. And we don't want to, one of the issues is sometimes I've seen them where these are stuck in a corner or they're put in front of a heater or something, so they're over or under responsive. They're not sensing what the animals see. The other is if you have windows in a building, you have to shield them from sunlight because you can get radiant heating of that sensor, so it's not actually sensing the heat of the building, it's sensing the radiation heat coming through the window. So that's, of course, an issue. And I talked about overshoot and cycling. Well, sometimes that's caused by heaters that are too large. So that can be an issue. So we could either stage heaters, like I previously showed, so they're not all coming on at once. Or the other thing is in some cases, some heaters have what we call throttling valve, where you could reduce the output of that by turning the amount of fuel that can go to that. So this is an LB White picture from LB White, and then Modine is another popular heater. They actually have a two-stage valve that can be have 50 or 100% output, so you could do it that way as well. So you could take the one heater and make it into a two-stage unit. As animals grow, here's, we've got a litter of newborns up to nursery age or finishing age. The energy or the heat required or the temperature set point drops by the week, typically. So in this case, it's about two tenths. I think it's 2/10 of no, I don't. We want to adjust it no more than 2 degree Fahrenheit increments. But this is, about 5 degrees a week roughly through here, through the age, until they get down to about 50 or 60 degrees. So we can set controllers up to actually automatically do this. That controller can be set up so it adjusts based on the age of the animal that we have. Creep heating, that was about 11% of our cost, and I often get people saying, is there anything I can do to reduce the cost of those heating lamps I'm using? And, typically you can't do a whole lot, but I'm going to show you a couple of options here. One is many creep heaters, they'll either have a spot in the floor where they have the heating elements inside the concrete, or this is an example of a heating pad that's electrically heated that you can put on a floor. So they can be electrical or hot water. The other thing we use is heat lamps or radiant heaters. Those are another types. The biggest thing here is, one, to have them thermostatically controlled, so we're not overheating or underheating. The other option to do is to do what we call hovers. Basically a little crate or a little, if you're familiar with the dairy industry, we use hutches. It's basically like a little hutch inside the barn for the animals. So here we've got some heat lamps over this, but we got a little space so that you're keeping that heat in that area. Here's another option where they just put a board over top of the area where the piglets go. They've got a little mat on the floor, and I think they actually have some curtains here. In the article, it talked about having some curtains where they get into this little area where they can go lay, and there's a heat lamp in there. So you're trying to help hold the heat into that area. So these can, almost cut your cost of electric and gas by 40–50%. Part of it is because you're not losing the heat from this. You can run the barn at a lower temperature. The sow only needs 50–60 degree temperatures versus the piglets they need 90–95 degrees in that first week. So, and the study that this was taken from the Minnesota study, they said there was a slight loss in survivability, but in their case it was still way above the industry standard. But And this can also be used for nursery piglets, and I've got an example of that here where we have bedded hoovers. So, this is just straw bales with some boards over the top to reduce draft, and lots of bedding where the animals can go in here and basically burrow into that straw for warmth. So that's another way to cut costs. We don't really need to heat if we give them enough bedding. Now to move on to poultry, and running a little low on time here, but we'll get through this. So here in poultry, again, like swine, we got a big portion of our costs are feeding. So anything we can do to increase feed efficiency is going to have a positive role. And again, our actual direct heating inputs are very small in comparison. Okay, the first thing we're going to look at is litter or manure management for this. We have bedding, it's going to give off ammonia, especially with poultry. So the question is, it's often done is they come in, they leave the last litter in there, they may stir it up a little bit, and then they put some new bedding on top and run a new flock on it. Well, that old bedding is going to keep giving off ammonia, and that's going to be the requirement to ventilate is because of that ammonia. So anything we can do to get better air quality is usually going to have a positive effect on bird performance, either weight, livability, condensation, that has to do with slaughtering and them having a disease or whatever, and feed efficiency. So here's a graph looking at if we reuse the litter, at day one we're starting way up here. If we put fresh bedding, we're starting way down here. So we've got a huge gap here where we have to basically supply that with heat in order to overcome our requirement to get good air quality. Once we get down a week out here, then they kind of come together because the birds can handle a little less quality of air. So here's, depending on your average outside temperature, what the heating amount of fuel you require, and the cost of that. So right now, LPs, I don't know, $1.50, $1.80, somewhere in that range, depending on where you are. So during the winter months, that could be close to $1,800 to $1,000. Depending on your temperature. We're going into warm weeks, so then we might be off this graph, but it'll be somewhere in that area during the winter months. So then the other question is, what's the cost of bedding? Because in this case, we've got I think it was a 40 by 500 foot building. So we got 20,000 square feet. We need 24 tons of bedding, $70 a ton. That's going to be almost $1,700 for that. Well, if we can get, 2% increase in feed conversion to get that bird to 6-pound weight, that's a feed saving of $1,600. So, this in itself almost pays for itself right there, and then you get $800 to $1,000 in savings on fuel cost. That's your profit basically. So that's not a bad investment, and this is over, typically it's 6 to 10 weeks to raise those birds, depending on the species for a broiler. So here's an example of, cumulative emissions of ammonia. If we're reusing litter, we're starting at a higher level versus if we're got new bedding, we end up basically saving it down here just to reduce that ammonia emissions. The other place in a layer house where we're doing eggs, they often use manure belts or that's becoming more popular, to get the manure out of the barn. So the question is, how often do you run those? You can run them every day, or you can run them once a week. And this graph shows that the ammonia emissions based on how often we run that. So the more often, or the sooner we get that out of the barn, the better the air quality is going to be for those birds. Now, in the poultry industry, that manure is worth something because it's high in nitrogen. Excuse me. So they often dry it and sell it as a soil amendment. So, especially to organic growers. So there's a couple ways they do that. One is we could use the exhaust air to dry the manure. So we've got some kind of racking system. We run that air through to dry dry the manure. Or the other way they do it is forced air blowers. So there's a possibility to reuse some of that heated air for another purpose before we exhaust it to the exterior of the building. The other way to do is chemically treat the litter, the used litter, with something that'll bind the ammonia. So alum is one, and ferric sulfate is another one that's often used. And you can see down here, it basically has a similar effect as new litter in there. So again, it's going to be the cost of that versus what the heating cost would be. So that's another option to do that. For heating systems, one thing I'll point out is to calibrate the sensors and controls. If we're getting false readings, we could either be using too much fuel or have too cool of an environment. So that can, stress the heat birds or be too cool. When it's cold, they're going to eat more to provide that energy. So either way, we could have issues. So making sure that the temperature controllers are correct. I kind of already talked about that. Make sure these sensors are measuring what the animals are exposed to. And then the maintenance of the heaters. They need to be cleaned annually, possibly more often, depending on the environment. If you got a dusty environment, you may want to clean them more often so you don't have dust build up on the heat exchangers that insulates them. Gas valves, check those. Igniters to make sure they're working properly. So that's all important. With heating systems, we want to make sure we're distributing the air uniformly. That's a requirement. If we're not, we could have variation. So here's a chicken house they did a study on, and they found the average was okay in their average feed intake, but there were cold spots and hot spots. So when it's hot, they eat less. When it's cold, they eat more. And what it led to was a wider distribution of egg sizes, which is not conducive to egg-laying type industry, because they want very uniform product. Otherwise, they have to start sorting them more. We want to avoid putting heaters next to fans. This may be a summertime exhaust fan, but if there's a wintertime exhaust fan, it's just not a good placement, because you basically can be shortcutting the air coming in and out. And then we want to replace old brooders with newer, more efficient ones. And we've got some pictures here of, this is on the left, we've got the old style that covers a smaller area, and a newer style that covers a much wider area. So and this is an infrared camera picture. You'll get better distribution of animals and not get you can see here we've got chicks. All the chicks are under here, and there may not be very many out in this other area. So this way we can distribute the birds out in a wider zone in that area and get better utilization of the space in the building. Here's an example on the upper left here of an air leak. So I love this. You can see the dark color here. Those are air leaks coming under the sill of the building. And you can see that the chicks have moved away from those areas. So that's an unplanned air leak that can cause stress on the animal, cause increased feed intake, etc. And then over here we've got an example where we don't have enough heaters, and we've got the animals clustering to keep warm in the middle of the building. They're trying to find the warmest spot in the building because they can't all fit under these brooders. So that's just an example of you can have too much or too little. Again, chicks, this is looking at broilers. As they age, the temperature requirements go down, so we can have that controller so it programs that in for that 3/4 of a degree reduction in heat per day over the 6 weeks that they're being raised. And one thing to point out, this temperature is floor temperature. Basically, it's 2 inches off the floor is where we want to take this temperature versus the building temperature. So we really want to heat the floor and keep that microclimate near the floor because that's where the birds are. They're not at 6 feet up where our heads are. They're down on the floor. So anything we can do to make that microclimate down there is better. Now, typically they're not using floor heating because the litter basically is insulating the floor to not allow that heat to come up fast enough. Ventilation systems, we need to make sure we have enough capacity for winter and summer, so we need to be able to adjust those fans to meet those requirements across that wide range. We need to have adequate air change to avoid condensation in the winter, either on the walls. So, depending on the wall insulation level, maybe 75%, maybe less than that. So if we've got the walls insulated well, that'll help. And then maximum cooling effect during the summer. And we're going to talk about tunnel ventilated here in a second. Maintain the proper static pressure. That's usually what we can measure to make sure we have uniform or the proper velocity of airflow and distribution of air through the building. And the other, from a decision standpoint, is making sure we're making good management decisions on that. So in summertime, we may have, it may get cool at 9 o'clock at night. So, if you looked at the temperature setting, it may shut the fan off, but those animals may still be stressed from being overheated during the day, so we may want to continue doing some cooling at night to do that, to pre-cool them for the heat of the next day, essentially. Ventilation rates, again, will vary depending on the size and age of the animal. I'm not going to spend a lot of time on that. So what I want to get to is a type of barns. We have cross ventilation and we have tunnel ventilation. And one of the things to look at these is the airflow or the velocity of the air is different in these buildings. So if I take a 40 by 400 foot building with a 10-foot ceiling and I calculate it out, I got 100,000 CFMs in this building. If I calculate out the airflow across the cross-section of the building, cross-flow barn, I've got 25 CFM, or 25 feet per minute, versus a tunnel ventilated, I have 250 feet per minute. So that's the airflow if I'm standing in there and I've got a anemometer. That's the airflow that I would measure. Well, this is wind chill, basically. If we can create a wind chill, we're going to get more cooling. So this looks at the cooling effect of air velocity for chickens. So, if we're up here in the 25, we're going to not get much cooling at all versus the 250 down here. It's more like 78. So even though it's 90 out, it can feel like it's 12 degrees cooler. So if we could actually increase this air velocity a little more, we could get more cooling. So that's one reason tunnel ventilated barns are preferred for cooling versus a cross-ventilated barn. In some cases, some areas, I can get good ventilation with natural ventilation. It doesn't take a whole lot of wind sometimes to get good air exchange. Now, I won't have the velocity, but I may get the air exchange. So it's capable of bringing fresh air in. So, spring, late spring, early fall, this may be adequate. One of the issues sometimes can be is to make sure my roof is insulated, because sometimes the sun on this roof will actually provide radiant heat down into the building. So we need to insulate that roof to actually help with cooling in some cases. So here's an example of, depending on how far the curtain is opened, as to what the ventilation is going to be, or the number of air exchanges on that. So if I have a higher wind, my curtain doesn't have to be open as much to get the air exchange versus a lower wind speed. Kind of running through here because we're running out of time, but I want to get to these. So anecdotally, stirring fans are going to be less efficient than a tunnel ventilated barn because of that cooling effect on the birds. So, you know, in some cases we may have people that have stirring fans. They'd be better off converting to tunnel ventilated barns because of the cooling effect. A couple of quick slides on dairy. If we look at dairy, basically almost 50% of our energy requirement from an electrical standpoint is going to be ventilation and lighting, with each about 25%. So in dairy barns, we can use natural ventilation with or without mixing fans, or mechanical ventilation fans, so tunnel ventilated or cross ventilated. You know, if we're doing naturally ventilated, we usually want wide side openings and open ridges to get that airflow through there with few obstructions. And then we put our mixing fans down the barn to do that. Mixing fans are usually these axial fans, but we can also use high volume, low speed fans. They're like a big paddle fan overhead. They can also be used. We use axial fans. Usually we have multiple fans are usually spaced in 2 to 3 rows about every 30 to 40 feet apart. So we can end up with a lot of fans in a building in a hurry. When we use these HVLS fans, as they're called, usually using a 20 or 24 foot fan in a dairy barn. Low speed, we need fewer fans with less horsepower, but they also do lower air velocities. You might have, 3 to 4 miles an hour wind, basically, versus with a high-speed fan, it might be 10 to 12 miles an hour. They do a very good job of mixing. They use variable speed controls, so you can drop the speed fan down. When you compare them to what we do with mixing fans, there is an energy saving about 4.3 kilowatts per hour. So there's a savings there. The question we have is whether they provide the cooling effect for them, and there's debate about that. Tunnel fans are very often used, so you can take a stall barn and make it into a tunnel ventilated barn or a freestall barn. But cross ventilated barns are increasingly used. Well, here's a picture of a tunnel ventilated. They can be a curtain sidewall, and the curtains are pulled up when we want to tunnel ventilate, and the fan's on one end. Cross ventilated barns are relatively new, last 10 years or so. They usually house multiple rows of cows, and then they'll have these baffles in them over the cow beds, because the air velocity is affected by the cross-sectional area. So if we plug some of that, then we've if we take this and divide this in half, then we've doubled the wind speed through this area, even though it's less in between. So we can get the cooling effect across the cow bed by putting in these baffles. These tend to be a lower pitched roof building, and then we use these baffles. Now, one thing to concern is that we have to run fans and lights year-round in these buildings. It's not, if you got curtain sidewall, you can open them up, but you can't in these type of buildings. So we've kind of roughed out here in Wisconsin. It's going to depend on where you are. We'd use about a third more energy with this type of building than you would with a naturally ventilated barn with stirring fans. However, you really have to look at what the milk production increase is, and we haven't had a good study on that to see if the milk production increase covers the cost. They can be used with evaporative pad cooling, so you can use humidification to reduce the air temperature during the summer, so that's an advantage. We can get some cooling depending on your humidity level, your ambient humidity level. In summary, energy conservation can result in higher profitability. It can be achieved by good design, operating within optimal conditions for the type of animal. We can use natural ventilation when conditions permit, usually in the spring and fall, sometimes during the summer, depending on where you are. Tunnel ventilation is probably best for summer ventilation versus cross flow, depending on the type of structure. And we should avoid higher static pressures. And indirectly, we want to improve feed efficiency. That's going to increase our, reduce our costs. So if we're looking at new fans, we want to make sure they're high efficiency. Go to Best Lab. For ventilating, we're ventilating because of ammonia usually, so that's going to increase depending on the amount of manure in the facility. Creep heating or hoovers can reduce heating costs, and fan maintenance is really important. So with that, I'm going to end, and we're kind of right at the end of the time, but I'll entertain any questions you have. If you don't think of one now, you can email me. This was recorded, so if you want to come back at a later date and review that, you will get sent the link as soon as we're done here. Any questions? Well, hearing none, I guess we'll call it a day, and I appreciate your attendance.